Good morning, ladies and gentlemen. I know you've been anxious for more math videos, and well, I'm here to deliver. We're going to continue with the concept of differential equations and specifically exponential growth and decay. And we're going to see, three problems that look very different, but really use all the same skills. Okay, so we start out with this problem. You invest money so that it compounds at a rate proportional to the amount you now have. Let's say you invest some money at 8% annual interest. Write the differential equation. By the way, DEQ is just shorthand notation for differential equation. So write the DEQ, which states the above. Then solve it for any initial investment I. Okay. So the very first sentence really tells us how we should set up our differential equation. Okay, so we invest some money so that it compounds at a rate proportional to the amount you now have. All right, so what does that mean? So I've gone ahead and I've actually kind of solved these problems ahead of time, but I'll sort of number the steps. So what this means is I'm going to define some function a of t to be the amount of money at time t. All right, and we are told that our initial amount of money is I, right? That's what this, oops, not a good, and that's what this information is telling us right here. All right, so if a of 0 equals I, that means 1 year later, the investment will have grown by 8%, or in other words, the amount of money you will have in that account will be 1.08 times I. Okay, so that's great. That's how we can use annual interest. I can tell how much money I'll have at 1 year, at 2 years, at 3 years, so on and so forth. But these are just very discrete time periods. What if I'm not thinking of keeping my money in this account for an entire year? What if I want to know how much money I have at any particular instant in time? Okay, well, knowing the annual interest rate doesn't help us explicitly. So what we need to do is solve a differential equation that will allow us to find the amount of money we have in this account at any instant t. Right, and the way we do that is the following. So we start with the differential equation. And this is just, again, from that very first sentence that says the amount of money you have at any point compounds at a rate proportional to the amount you now have. So the rate of change in my amount over time is equal to some k times the amount I have at that particular time. All right, and now from here, it's just like what you saw in the last video. We're going to separate the differentials and we're going to integrate. So this is what I would do next. Separate, integrate. Okay. Step 3, this becomes ln absolute value of a is equal to kt plus c. By the way, I'm going to move kind of quickly through these steps. Obviously, since it's a video, you can kind of like pause and think. But if you don't understand these steps, please come to SGI, which is held daily from 12 to 1. All right, and I post a link every day in the Google Classroom stream. Okay, so anyway, we have ln absolute value of a is equal to kt plus c. This, of course, leads to the fact that the amount you have at any time t is equal to c times e to the kt. All right, this is called a general solution. That's step 4, is a general solution. We now need to use our initial condition to solve for at least one of the constants, and then we have another condition. We have 2 conditions to help us solve for both constants. So start out with a of 0. We're told initially that a of 0 is equal to I. And based on step 4, a of 0 is also equal to c times e to the k times 0. This simplifies to be c is equal to I. All right, so this was what I did in step 5. Step 6, I just sort of rewrote the general solution with the updated information that c is equal to I, whatever you initially invest. Step 7, I'm now using the fact that 1 year later, that initial investment has grown by 8%. Okay, and so I have 1.08I is equal to I times e to the k times 1. And this tells me that k is equal to ln of 1.08. And finally, we have our particular solution. So if you invest any amount of money at an initial rate of, at an annual rate of let me rephrase that. If you invest an amount of money at an annual rate of 8%, then the amount of money you have at any point in time will be equal to this expression over here. So there you have it, and that's the solution to that problem. Again, these problems require you to sort of be able to interpret what the problem is saying to you, try to express it as a differential equation, and then from there, the solutions are very, very, very similar. Okay, moving on. All right, so we have this second problem, which says the downward acceleration of a man whose fall from a practice tower is being slowed by a parachute. And that acceleration is given by a equals 32 minus 10v. So that's an acceleration function at any given point in time. But notice that it's actually written as a function of velocity. Okay, and our job is to show that the velocity function over time is equal to 3.2 times 1 minus e to the negative 10t. All right, and we're also told that the initial velocity is 0. So what I like to do is just sort of write out the information given. Well, v of 0 equals 0, that's easy. We also have the fact that a of, I guess this is technically a of v, because no, I'm going to leave it as a of t. Sorry, it is a of t because velocity itself is a function of time. Right? And so acceleration is, of course, the rate of change in velocity over time. So instead of writing this left side as a of t, I can write it as dv dt. So expressing it this way allows me to sort of see what's changing as time moves on, and it is velocity that is changing as time moves on when we're talking about an acceleration function. And so we can re-express this as dv dt is equal to 32 minus 10v. Okay, now just over here, you might be tempted to separate this problem in the following way. You might want to try to like subtract 10v from both sides as your first step and express it this way. But you'll notice that if you do this, you still have both differentials on the same side, and this is not going to allow you to integrate in order to find the antiderivatives. So this is not an option for separating this differential. What you actually have to do is just treat this right side as one big expression and divide both sides by that expression, and then multiply both sides by dt, and you'll have this expression over here. And then, of course, you have to integrate. Once you separate those differentials, the very next thing you're going to do is integrate. So to number the steps, we started out here. We re-expressed over here, separated over here. And now to integrate this left side, I'm going to use u substitution. So that denominator is going to be what I call u. So I'm going to let u, let me zoom out so you can kind of see all the steps. I'm going to let u equal 32 minus 10v. That implies that du is equal to negative 10v, which also implies that du over negative 10 is equal to dv. All right, so wherever I see a dv, I'm going to replace it with du over negative 10. And then that's what I've done here. That negative 1/10 I've actually pulled out front, which you can do when you're integrating. And when you're differentiating, you can pull the constants out front. So that's what I've done here. So the left side now is just simply negative 1/10 integral of du over u, and that is still equal to the integral of dt. All right, step 6 is now to integrate negative 1/10 ln absolute value of u is equal to t plus c. All right, and of course, I do want my expression or my equation. That's a terrible 7. I want my equation in terms of v. So I'm going to replace u with v, with my expression of v, I should say. So this becomes negative 1/10 times ln absolute value 32 minus 10v is equal to t plus c. All right, this kind of looks like it looks a little messy for sure, but it's not that big of a deal. All we're doing now is going to solve for v. So the first thing I did was I multiplied both sides by negative 10. I want to point out here that this constant, negative 10 times c, is just also another constant. So from this step down to the next step, I just rewrote it as c. You can call it c1 if you want, but really it's not necessary. A constant can just be expressed as c. All right. If you really want to keep track though, feel free to call it c1. Just keep in mind that negative 10 times a constant is still a constant. All right, so from here, this is step 8. From here, I apply e to both sides in step 9. And again, I'm skipping a bunch of steps now because this is just exactly what we saw in the previous video, just solving a differential equation for exponential growth / decay. So I'm skipping steps. If you need to fill in the blanks, either come to SGI or just watch the previous video. But at this point, in step 9, I have 32 minus 10v is equal to c times e to the negative 10t. Actually, at this point, I'm just going to go ahead and use my initial condition. And remember, that initial condition was that velocity is 0 at time 0. So I go ahead, I plug in the initial condition, and this will tell me that c is equal to 32. All right, now ultimately I'm solving for v. So in step 11, I sort of just rewrite step 10, but instead of c, I write what I discovered about c, and that is that it's equal to 32. And from here, there's just some algebra going on in step 12 to solve for v. And finally, after all that, we do have our expression for velocity at time t. And you'll see if I scroll up that what we solved does indeed match what we were trying to solve. So the goal of this problem was to show that velocity is equal to 3.2 times 1 minus e to the negative 10t. And that's what we have. Cool. So again, vastly different description of a problem, but the work involved is very, very similar. All right, very, very, very similar. Okay, we'll do one more example, and then I think you'll have enough to sort of work on your own to complete the homework. This problem involves a concept that you are probably familiar with, especially if you took pre-calculus. It's called Newton's law of cooling. You haven't seen it expressed this way, though. This is now actually how Newton's law of cooling was really initially conceived, and that is as a differential equation. So basically, Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and the outside air. So the rate of cooling of an object is proportional to the temperature difference between the object and the outside air. So this left side represents the rate of cooling of the object. Okay. So it might not be obvious, but actually this letter R, which is a function of time, they do, I'm sorry, they do tell you. R is the temperature at any particular time. Okay? So dr dt represents the change in temperature over the change in time. So that's the rate of cooling, and it is proportional to the temperature difference between the outside air and the object. Or sorry, the object and the outside air. So this right here is the outside air. And this right here, of course, is temperature of, in this case, Turkey. But it does not have to be Turkey. It could be anything that is just sort of cooling in a temperature controlled room. Notice, though, that the constant of proportionality is negative here, and that indicates that, in fact, the rate of change of temperature is actually sort of decreasing, or I should say that the temperature itself is decreasing. As time goes on, the temperature of the turkey is going to go down. Okay, that's why K is negative here. All right, so that's our starting point, and part A says solve the differential equation for R, then use the information, use the given information to find the particular solution. Okay. Again, very similar to what we've seen. Maybe the description is not similar, but the work involved is going to be similar. So here I'm actually going to sort of show the work explicitly step by step. I'm going to start out with dr dt is equal to negative K times 75 minus R. Okay. Separate these differentials. dr over 75 minus R is equal to negative K dt. And just like last time, I'm going to use u sub to integrate here. So I'm going to let u equal 75 minus R. This tells me that du is equal to negative dr. Or in other words, negative du is equal to dr. So wherever I see a dr in the expression on the left, I can replace it with a negative du. So that's what I'll do next. So the integral of negative du, so I pull the negative out front because it's a constant. And the denominator is 75 minus R, which is exactly what I defined to be u. All right, the right side is still, there should be an integral here. Sorry about that. And notice that I put the integral to the right of the negative sign. Again, negative, you can think of that as -1. It's just a constant. So I'm just going to pull out all constants. So we have the integral of k dt on this right side. Technically, k is actually also a constant. So if I wanted to, I could have negative k times the integral of 1 dt. All right. Keeping going. These negatives actually cancel. So I can just get rid of them. The left side is ln absolute value of u. The right side is just kt plus c. Okay, moving forward, running out of room, so I'm going to try to write a little bit smaller. So, of course, u is 75 minus r, so I'm going to do a few steps at once. I'm going to apply e to both sides, and instead of u, I'm going to write it as 75 minus r. So the left side is just 75 minus r. The right side is is big C times e to the kt. And again, if you don't know the step, if you don't understand how I went on the right side from kt plus c to c times e to the kt, watch the previous video because I do explain that in detail. But since I've already explained that in detail, I'm not going to do so here. So using the initial condition, because right now all we have is a general solution, but I want a particular solution. We're told that r of 0, moving forward, r of 0 is equal to 185. And this means that 75 minus 185 is equal to c times e to the k times 0. Simplifying, this tells me that c is equal to negative 110. Okay, a lot going on, but we're not done yet. Okay, just rewrite this as 75 minus r is equal to, instead of c, I'm going to write negative 110 because that's what we just discovered about c, equal to times e to the negative kt. And finally, this implies that r of t is equal to 110 e to the kt plus 75. All right, that is it's still a general solution because we haven't solved for k yet, but at this point, we haven't been given any more information to help us solve for k. So at this point, this is as far as we can get. You'll see in the very next step, we'll be given some more information that will then help us solve for k. But as of now, the temperature of this turkey at any particular time is equal to 110 times e to the kt plus 75. So let's move on. If the temperature of the turkey is 150 degrees after half an hour, what is the temperature after 45 minutes? So this is sort of a two-parter. We are given that r of 30 is equal to 150. Now it's r of 30 because if we go back here, the units of time that we're using are in minutes. Right over here, it says after t minutes. So if we're talking half an hour, that of course is 30 minutes. So r of 30 is 150. Now we could actually use that to say that 110 times e to the k times 30 plus 75. So this is my turkey temperature function at 30 minutes. And we're told that that's equal to 150. Again, I'm going to skip the algebra steps. So this ends up leading to the fact that k is equal to ln of 75 over 110, all divided by 30. And we can go ahead and just use an approximation, negative 0.0128. Actually, it really is best to use the exact solution, but just for simplicity, for your simplicity in viewing and my simplicity in writing, I'm just going to use this approximation. So this actually gives us now the true particular solution for this exact situation, and that is that R of t is equal to 110 times e to the negative 0.0128 t plus 75. And now to determine the temperature after 45 minutes, pretty simple. Take that equation, plug in 45. And you should get something around 136.929 degrees. If you're getting something slightly different, that's fine. There's going to be some pretty serious rounding errors depending on how many decimal points you use. That's why I do suggest for K going to no fewer than 4 decimal places. All right, moving on to C. When will the turkey have cooled to 100 degrees? So this is now a problem where we're going to solve for a time. All right, so again, it's useful to restate the particular solution. So 110 times e to the negative 0.0128 t plus 75. And we want to find the value of t that makes the turkey 100 degrees. So 100 is equal to 110 e to the negative 0.0128 t plus 75. And again, this is just algebra from this point. And I'm going to skip the algebra. But you should end up with t equaling something around, so let me do approximate. Since we are approximating that value of k, you should get something around 115.741 minutes. Okay. If you don't understand how to get there, please come see me during SGI one of these days very soon. All right, last but not least, what is the limit of the temperature of the turkey as time goes on? So basically, as time goes on, theoretically towards infinity, will this turkey just keep decreasing in temperature? If so, does that mean it'll go to a negative temperature? What does a negative temperature mean? Blah, blah, blah. So that's what this question is trying to make you think about. And the answer is not so bad. So let's take our temperature function. Right? You might be thinking, well, temperature is decreasing, and so as time goes on, should temperature just keep decreasing? But then obviously you say to yourself, I mean, the temperature, I guess technically could be negative, right? We do have negative temperatures outside sometimes, but do you think the turkey is going to get to a negative temperature? Well, let's analyze. So as t approaches infinity, the expression e to the negative 0.0128 t. Well, that expression can also be written as 1 over e to the 0.0128 t, right? Because of the negative exponent, I can just rewrite this as 1 over whatever the expression is. And as t gets really, really large, this guy in the denominator is going to also get really, really large. So this guy is really going to approach something like 1 over infinity. Well, 1 over infinity, of course, is essentially 0. 1 over a very, very, very large number is a very, 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 very small number. So we can use that information to say that, I'm just going to rewrite the expression again, 110 times e to the negative 0.0128t plus 75. You'll notice that the only expression that has anything to do with time is this e to the negative 0.0128t. We just discussed how this guy is approaching 0 as t approaches infinity. And so therefore, this entire term zeroes out. And so we can say that r of t is approaching 75. The calculus way of writing that, of course, is the limit as t approaches infinity of r of t is equal to 75 degrees. Okay, and there you have it. All right, ladies and gentlemen, those were just 3 examples of problems that I wanted you to see. Again, the descriptions seem very different. However, the problems, the solutions themselves are very much the same. So I hope that helped. Let me make sure I know how to stop this recording. And yeah, so I'm going to stop recording now. Please, again, if you're struggling with any of this material, come see me during SGI. We can talk it through, and I hope all is well. Take care.